Welcome to The Explainer. Today, we're talking about a force you feel every single second of your life. But figuring it out? Well, that was a 350-year epic. This is the story of gravity.
So, for thousands of years, humanity was kind of captivated by two huge and what seemed like totally separate mysteries. The first one is something we see every day, all the time. Why do things fall?
And the second one? Well, that was playing out way up there, in the skies. It was the silent cosmic dance of the planets. Why do things orbit?
You know, for centuries, we figured these two things, falling on Earth and orbiting in the heavens, were governed by two completely different sets of rules. Turns out, we were totally wrong.
So, let's dive into the one single revolutionary idea that connected everything. Alright, so for almost 2,000 years, our whole picture of the cosmos was shaped by models like Ptolemy's. And his big idea? It put Earth smack dab in the center of everything. Now this geocentric model, Earth in the middle, was eventually challenged by a much more elegant idea, the heliocentric model. That one put the sun at the center. It was a beautiful theory, but man, it got people like Galileo into a ton of trouble. Okay, so the next huge leap forward didn't come from some new grand theory. Nope, it came from data. Just raw data. Decades of it, meticulously collected by an astronomer named Tycho Brahe, and then crunched by his brilliant assistant, Johannes Kepler. So Kepler is just sifting through all this data, right? And he pulls out these three beautifully simple laws, and they perfectly described how the planets moved. The catch? He still didn't know why. First up, he just completely shattered this ancient idea that everything moved in perfect circles. Turns out, planets move in ellipses. Think of it like a stretched-out circle. And the sun? It isn't at the very center. It's at one of two special points called foci. Okay, second law. He figured out that if you draw a line from a planet to the sun, it sweeps out equal areas in equal amounts of time. Now that sounds complicated, but it's just a really clever way of saying that planets speed up when they get closer to the sun, and they slow right down when they're farther away. And his third law? Whoa. This one is just a stunning piece of mathematical harmony. He found that if you take a planet's year, its orbital period, and you square it, and then you divide that by the cube of its average distance from the sun, you get the same number for every single planet. I mean, look at this table. That last column is practically constant. It was like a cosmic secret code hiding in plain sight. So Kepler gave us the how. He laid out the rules of the cosmos. But he couldn't give us the why. That question, the big one, remained a mystery. Well, until an English mathematician named Isaac Newton had a thought, supposedly while watching an apple fall from a tree.
And here is Newton's stroke of pure genius. He connected those two big mysteries we started with. He asked a simple but profound question. Could the force that's pulling this apple down to the ground be the exact same force that's keeping the moon locked in orbit around the Earth?
I mean, think about it. That's a radical idea, right? But for it to work, this force had to get weaker the farther away you get. It just had to. Otherwise, the moon would have crashed into us ages ago. And Newton, being Newton, didn't just guess. He proposed a very specific mathematical relationship. He figured that if you double the distance between two objects, the gravitational force between them doesn't just get cut in half. No, it drops all the way down to 1/4 of its original strength. And if you triple the distance, it plummets to 1/9. It gets weak fast.
And that right there, that's the famous inverse square law. It is the absolute heart of his universal law of gravitation. And with one single equation, Newton did it. He united the falling apple and the orbiting moon. He brought the heavens and the earth under one single elegant rule.
So this universal law, it actually has some really surprising consequences for us, right here on planet Earth.
We all kind of think that gravity just gets weaker the higher you go, right? Well, yeah, but here's a wild consequence of Newton's law. Gravity is actually at its strongest right here, on the surface. So it gets weaker as you go up, but it also gets weaker as you go down into the Earth. Why? Well, because as you go deeper, more of the Earth's mass is actually above you, pulling you up and kind of canceling out some of the pull from what's below. Okay, so if gravity is always pulling everything in, that brings up a new question. How does anything, like a satellite, stay up there? And, the big one, how do we ever leave Earth for good? It all boils down to this really cool question. Let's go back to that apple. How fast would you have to throw it so that it just never comes back down?
Well, the answer has a name. It's called escape speed. And for Earth, that speed is an absolutely mind-boggling 11.2 kilometers per second. That's about 25,000 miles per hour. To put that in perspective, you could get from New York to LA in about 6 minutes. If you launch anything slower than that, it's either going to fall back down or get trapped in orbit. But if you hit that speed, you're gone for good.
And what's cool is this idea of escape speed perfectly explains other cosmic mysteries. Like, have you ever wondered why the moon has no atmosphere? It's because its escape speed is super low, only 2.3 kilometers per second. So over billions of years, any little gas molecules just had enough speed to, poof, drift away into space?
So, look, Newton's law was an absolute triumph. It told us how gravity works with such incredible precision that we can use it to predict planetary motion and send spacecraft to the edge of the solar system. But it left one huge, profound mystery unsolved. What is gravity? You see, Newton described the effect, but he never explained the cause. Answering that question, well, that would take another genius and a complete rethinking of space and time itself.